integrity. All right. So I'll do pretty much the same idea. I will begin to give you a formal definition of how it works. But as you may imagine, some of integrity builds on top of what we've covered already. So XOR may be a part of it. You see what I'm saying? So, you already now have like these Lego pieces of XOR and blocks, etc. And we're going to continue to use them to start to build other primitives and other more complex algorithms. So in this case, we're going to talk about message integrity. Message integrity. And in particular for this, a lot of people call it hash functions. They'll just say like calculate a hash or something like that, right? The idea with hashes, without getting too complicated right now, because you can have multiple algorithms to achieve this goal. But basically, you go from a sequence that's pretty long to a smaller sequence that is fixed. That's what a hash is. Do you see what I'm saying? So you have an input, the data basically. What can the data be? The data could be a movie, or it could be, something, code that you're downloading, programs, etc. Whatever, anything that can be zeros and ones basically, right? Because it's digital, it's something on a computer. So you go from something that is a message, for instance, here, to the actual hash value down here, okay? Where this one is much smaller and fixed, right? But basically this, which is actual data, should look very, almost random here, right? And, it can, and basically you need an algorithm that given this produces this, and it's very unique to that, such that if I was to just change one bit of this, even if it's a movie, the hash should be what? Very different. Does that make sense, guys? All right, so this is just kind of like the ideas. We will more formally come back to this, but this is pretty important, okay? So the input, right, can be anything, and it gives you something that's a little bit more fixed, right? And so we're going to need to define what this algorithm, how we could possibly describe this algorithm and implement it, okay? So basically, the objective of this is to want to make sure that our files, etc., have not been changed, okay? That's really integrity. So files have not been changed. Okay, so very, very important. This is actually very effective. That's the beauty of it. Now, this primitive, if you've ever heard of signatures, maybe some of you have heard of like digital signatures in cryptography, we will need hashes and several other things to build a signature. Okay, so it's part of it. So it's one of the primitives of more advanced cryptographic techniques. So the basic approach is to provide a MAC, which is a message authentication code. Okay, so the basic approach is to provide a MAC. Provide a MAC. You'll see this a lot in the labs. So the labs have like MAC this, MAC that, and it basically just means a message authentication code. So authentication code, okay? And that, well, basically would be the hash value. Okay, later on also we will learn that hashes have applications to other areas beyond cryptography, like malware detection and those kinds of things. But we'll talk about that a little later. All right, so how does it work? Again, Bob and Alice. All right, so we have Alice. Over here, they want to communicate across the insecure internet. Same idea as before, but in this case, all they care about is integrity. So actually, they don't care that people can read the file, that, you know, it's perfectly fine. They're perfectly fine with sharing this code. Maybe it's some code that they wrote. They want people to use it. All they care is that people, when they use it, they know that it hasn't been tampered, right? Yeah, please. Huh? It is. I mean, it is within the realm of it, because you're achieving one of the, well, it is encryption because we're jumbling the data, right? To create the hash, we take the original data and produce this thing. But the objective that we're meeting is not confidentiality. It is integrity. You see that? That has a value. Just because you know what it is doesn't mean that the hash is not important, because it tells you that it hasn't been tampered. And that may be the thing that you care about in that situation. You see that? It is part of cryptography. And it is definitely part of like digital signatures and other things that are much more advanced. Hashing has uses outside of cryptography. I'll give you that. Yep. Make sense? Yeah. All right, good. So we have this. So we have a few minutes. So we've got basically a message M. Right, so I'm just going to say M over here. And what we want to do is we attach to it, you know, a sequence of bits that we can call the tag, for instance, or the hash, or whatever it is. But this is really just, you know, 100 bits or so, 128 bits, whatever it is. Where do you get these 128 bits? They are produced from this message, and they are unique to that. Such that, as I said, if you change even one bit of this message, the hash should be completely different. Got it? Completely different. Not just a little bit, completely different. And that is what makes a good algorithm. You can have a key also if you want to, because at the end of the day, it's going to be based on an XOR operation. So you can XOR anything, right? And so you can have a key in some of the cases. So Alice will use a Mac. We'll use some algorithm. Let's say in this case, I'm using this term tag as a generic term, could be the hash. The algorithm, let's just say S, and this can have a key and the message. That's it, okay? Where the message in terms of length is much bigger than the tag in terms of length. Okay, so that's an important distinction. So you could take a whole movie and hash it into like a 256-bit sequence, for instance. Got it? All right. So that's the formal definition. And then Bob, so that's Alice produces the tag. So this is Alice, right? Sending the tag in that direction. So now Bob, oh, and I ran out of these things. So let me go back here. It only gives me 20 for some reason. Anyway. Okay, so we'll wrap up with this one here, just to show what Bob does, basically. So we sent the tag, right? And so now Bob's needs to verify, basically. So Bob will basically verify by having some other algorithm, okay? And what are the parameters for this algorithm? Since we used a key in the previous one, right, we need it here. We also need the message, right? And then we need the tag, because that's what we're going to receive. Do you guys see that? So in the previous example, we had a key and a message, run it through the algorithm, and we get the tag, right? Then we send the tag with the message. Do you guys see that? And they have already a shared secret key. So then over here, we've got key, we've got the message, we've got the tag. Notice that the message is not encrypted, because we don't care about that, right? We only care about integrity in this particular case. And then what should be the output of this algorithm? What do you guys think? We already know M. Why M if we already know M? What do we care about here? V is the algorithm. So V is actually what we're doing. It's a function where we give it K, M, and the tag, and it gives us something. What do you think it gives us? We already have the tag. It's right there. What's the output of this function? What? The tag is the hash.
Oh, no.
What is I?
Like the authentication.
Okay, you're onto it. You're onto it. So
It's the verification.
it's a verification. So verify, not verify. That's what you're getting. Yeah, that's what it gives you. So it checks out or it doesn't check out. Do you guys see that? Yes or no? That's it. Does that make sense? That's what you do, because if you think about it, and we'll wrap up with this, again, you have a key if you want, right? You take the message, run it through some algorithm, you get the tag. The tag is much smaller than the message. And then on the other end, Bob needs a verification algorithm, right? It's got to have a key because they used a key. Got the message, which is plain text because you don't care about confidentiality. You receive the tag, and what you're verifying is that it matches. So basically, it's almost like, say, you take the key and the message, regenerate the tag, and compare it to the tag you received. If they match, boom. Yes, true or false. Got it? All right. So we can stop here for today, and then we will elaborate more on these ideas. But keep in mind, I've already given you integrity and symmetric key encryption. So we're starting to build up more.